First, for simplicity, we just assume all the manifolds are connected, oriented, and compact at least. So I will not write down these assumptions again for the whole talk: connected, oriented, and compact. And actually, for most of the time, they will be closed, but there will be maybe 1 or 2 times they will not be closed. OK, so the title is called Virtual Domination of 3 Manifolds. I guess everyone knows what is a 3 manifold. And I assume everyone knows what that virtual means. Virtual means just for some finite cover, certain property holds. And I guess so the only thing which may need a little bit of explanation is something called domination. So if we have maybe we can talk about something very general. For 2 n manifolds, maybe m and n. So if there exists a non-zero degree map, from m to n, then we say M dominates n. Say M dominates n. So the existence of such a non-zero degree map has some corollaries, and which more or less gives some hint that says that M, the domain, the source, is kind of more complicated than the target, at least in some vague sense. For example, you can say, I guess the simplest one is just the B1 or maybe BK of M. Oh, sorry, I guess I assume closed here. BKM is greater or equal to the BK of n for any Betti number, of any dimension. BKM is greater or equal to BK of n. And also the pi1 of m suggests, it may not suggest the whole fundamental group of n, but at least it suggests a finite index subgroup. OK. So virtually finite index subgroup is just the fundamental group itself. If you do the virtual function. And I guess if you restrict to dimension 3, at least I guess if n is taken, it implies I guess m is taken. If m is irreducible. This is something which is kind of not very hard to prove. But there's something really hard, which actually, I guess no one knows the answer. So still n is equal to 3, and maybe degree of f is equal to 1. We can ask whether genus, the Hilgard genus, whether the g of m is greater or equal to g of n. I guess this is an unknown question, and I guess it will be very hard, at least when the genus of n is equal to 1 is already, I guess, proved by Perelman. Because, you know, yeah, I guess so. So I guess for any genus greater than 1, it is not known. is equal to 1. Oh, sorry, m is equal to 1, sorry, yeah. So G, yeah, sorry. So, yeah, G of m is equal to whatever, anyway. So for this question, as we know, it is completely unknown when the genus are bigger than 1, I mean. Okay, anyway. So I guess for the non-zero degree maps, one of the most important invariant is the simplicial volume. It's just saying that the simplicial volume of M is greater or equal to the degree of F. Maybe take absolute value times the absolute value of, the simplicial volume of N. And we know that, say, for hyperbolic manifold, the simplicial volume is just proportional to the hyperbolic volume. I guess this will be something we will just come back later in this talk. So here are some naive questions we can ask. So if we are given closed manifolds and n of the same dimension, of course, then we can ask whether dominates n. Okay, and I believe it's very easy to get some examples says M does not dominate n. Say whatever, say the first Beatty number of M is smaller than the first Beatty number of n, or the simplicial volume is smaller than the simplicial volume of n. So if simplicial volume is smaller than the simplicial volume of n, then no. Okay. So this is some very easy stuff. But the question is, what if we pass through finite cover? Of n. I guess at least for low dimensions, I mean really low dimensions, this is pretty easy. When n is equal to 1, I guess we only have S1, which virtually dominates everything. When n is equal to 2, I guess any hyperbolic surface closed virtually dominates everything. And then there's a theorem by Gafflin, who says that, let me write it here. It's in 2012, I guess. For any dimension, there exists a very explicit closed manifold n, which virtually dominates any n-dimensional manifold. Any closed n manifolds. And since we will just restrict to dimension 3 just maybe in 1 second, so maybe in his example, in the n is equal to 3, I guess you can take the double of maybe bromine ring complement. Of course, if you take any manifold virtually dominate the manifold Gafflin constructed, then it also virtually dominates everything. So once you have one example, you have a family of examples. They take connected sum is anything you prefer.
Is it obvious that you can't take something hyperbolic to have this property?
Sorry?
Is it obvious whether can you take something hyperbolic to have that property?
You mean in dimensions?
3.
3. Yeah, that's more or less what I. Yeah. He also showed that when n is equal to 3 or 4, there's some hyperbolic ones satisfying this virtual domination property. But when n is larger, he did not show that. And I guess today my theorem is saying that for any closed hyperbolic string manifold, M and any closed string manifold. So I'm just claiming any closed hyperbolic string manifold virtually dominates everything, but there's a little bit more detail. There exists a finite cover M prime of M such that so-called M prime 2 dominates N. 2 dominates means there exists a net F from M prime of degree 2. Okay, so given this theorem, I guess the first question you can ask is why degree 2, not degree 1 or whatever?
So I'm assuming the covers of M prime is very large degree.
Yeah, and there's no control.
So then, actually a kind of a complementary question, which maybe just ask it now, so it's not to derail you later or something. Supposing I wanted to go sort of in a different direction, say I wanted the ratio of the degree divided by the degree of the cover, the degree of the map divided by the degree of the cover, to be as small as possible. Is there any reason to suppose that you couldn't get as close as you like to the ratio of the volumes?
Actually, this is something I will talk maybe in the last 10 minutes, although maybe it's not very satisfied answer, but there's something I can say about that. Okay, so let's come back. Still the question, why degree 2? Okay, so actually the first version of this theorem is just saying that there is some non-zero degree map. And at that time, I think it's pretty good. And then Ian taught me some theorem about universal orbifolds. And then I could reduce it to degree 2. The results look stronger, but it seems this 2 looks quite strange. But there's some reason for that. And that is, I will explain why we have 2 in maybe, hopefully, 15, 20 minutes, and as from some work of Liu and Markovich. Okay. So given this theorem, just as I said, the first question is, question 1 is just, what about degree 1? And I guess, I don't know. Somehow, because in the proof, I'm kind of lazy and do not work really hard. Maybe someone works really hard, he can get degree 1. But maybe it needs some new idea. And the question 2 is just, what about, we do not assume M is hyperbolic. We just assume the simplicial volume of M is greater than 0. So the simplicial volume is greater than 0 implies if you first do prime decomposition and then do JST decomposition, you get some hyperbolic piece. And the hyperbolic piece should have some kind of virtual, its finite powers is kind of a big family which somehow should satisfy many nice properties. Okay, so I guess there's no terminology which is difficult in this theorem. So maybe let's talk about something about the proof. So to prove this theorem, at certain step, you need to construct some non-zero degree maps, of course. And actually, the way to construct this non-zero degree map is more or less the most stupid way you can do. Say, if you want to construct a non-zero degree map from any n manifold to just the n-dimensional sphere, what you can do is just take a ball in that manifold and pinch everything else and do certain self-degree n map on this sphere. So the construction in the proof of this theorem is more or less the same. So I do not really want to call it lemma. It's just kind of an observation. So I will still more or less reserve the m prime, and n for the manifolds in the statement of that theorem. So we first give n in the end with a kind of nice handle structure. Actually, we do not need nice here. And so the observation itself do not need, so this handle structure satisfies any property, but in the proof, we need the handle structure satisfy some property. And let the n2 be the union of 0 and 1 and 2 handles. You can also say give an Higa splitting and take the one of the handle and then add the few attaching disks. It's the same thing. And if the m prime has a codimension 0 manifold, submanifold, some called maybe L, such that there exists a degree k map from L and its boundary to the n2, and still boundary maps to boundary, so that we can define some degree homology relative. I guess L is still connected. But anyway, non-connected is still the same. Then there exists a degree k map from m prime to n. So the proof is just follow the first this degree k map on the L and pinch everything else. Proof is very simple, but this is the way I will prove that theorem. So to apply this observation to prove that theorem, so we need to give n a handle structure. And we somehow need to find a finite cover of M, which has a codimension 0 submanifold satisfying certain property. Okay, so basically two things we need to do. So what we can do now, maybe I just say a little bit about a few steps we can do in the proof. There may be 4 steps. Step 1, I guess start from n, because I guess that final cover should depend on n, of course. So just given a handle structure, give a nice, here we really need a nice handle structure. And actually, this nice handle structure given by the universal orbifold. Which is given by Hildin, Lozano, Montesinos, and Witten in 87. So I will tell you what is the universal orbifold in just maybe 5 minutes. And then with step 2, is just use. So somehow we just wanna put the picture of this handle structure of n into the hyperbolic stream manifold M by using certain tools to just exactly, more or less exactly put the picture here, the 0 and 1 and 2 handles in n, put them into the manifold, hyperbolic manifold M. So a little bit more specifically, use points and long geodesic arcs. And also something which is really important here, almost totally geodesic surfaces. So use these things. These are some 0-dimensional thing. This is some 1-dimensional thing, and this is some 2-dimensional thing. So they will correspond to the 0 and 1 and 2 handles or cells of n in M to just mimic the 0 and 1 and 2 handles or cells in n. So for this part, I guess the main tool is given by some guys in this room. I guess the first really important paper in this is by Khan and Markovich in, I guess, 2009. They constructed some closed, almost totally geodesic surfaces, perpendicular in M. And then Liu and Markovich constructed some almost totally geodesic surfaces with boundary, I guess in 2013. So we will use more or less Liu and Markovich's work to just get these almost totally geodesic surfaces we want. And more or less, here are some 1-to-1 correspondence points correspond to 0 handles or 0 cells. Long geodesic arcs correspond to 1 cells, and almost totally geodesic surfaces correspond to 2 cells. So for 0 and 1 cells or handles, they are just homomorphic to each other. For 2 handles or 2 cells, we really need to replace these kind of disks to these surfaces with high genus. space is not very even distributed. So we might move everything back here. Maybe step 3 is just put these parts together. Use the above parts to just build a immersed 2 complex. Actually, pi1 injective immersed 2 complex in Z immersed in M. And then the final step is just use Ian's result that the fundamental group of hyperbolic manifolds are Lerf to just lift this Z into some pi1, so to lift it to some embedded 2 complex in some finite cover. Lift Z to be embedded in some finite cover. Yes, that's our desired M prime of M. And then a neighborhood, NZ of Z, in the M prime is just the desired L in the observation here. So I guess it is ego, and I guess to state this theorem, we really always need to write down Y's name and maybe some other guys in. I guess the final step is in 2012, pi1 of hyperbolic 3 manifolds are Lerf. So I do not really want to explain what that Lerf actually means, but it more or less means pi1 injective immersed things can be lifted to be embedded. Although it's not 100% correct, but it's more or less 99% correct. Okay. So I do not want to go to the full detail of these steps, but I just maybe tell you about what is the universal orbifold and how to construct such parts to just build the immersed 2 complex. Okay, so let's first talk a little bit about universal orbifold. So it is a theorem proved just by those 4 people. I do not really want to write down all these names again. So for just for N3, just the closed-oriented 3 manifold, any N3. So there is a orbifold structure. N, which is a finite cover of the universal orbifold. Maybe I call it M0. So what is this universal orbifold? So I guess there are at least 2 very nice ways to describe it. The first way is to draw a Berkeley ring, which actually is really difficult for me. Okay, I guess this is a Berkeley ring. And you take just S3, but as underlying space. But the Berkeley ring is just a singular set, and all the singular points has index 4. So it means if you take a small disk intersecting with one of the circle, and then the cone angle in the center is just 90 degrees instead of 360 degrees. Or you can just look at, but let's first draw a cube, which is still something quite simple. And then we just paste the faces of this cube. But of course, not by the way we get the three-dimensional torus, but by some way which is just kind of folding on each of the faces. It seems it's not good, this direction. And then for each of these squares, you just do a folding here. So this is a piece of paper, you just fold it like this. Of course, if you just fold it in the Euro way, you get just the three-dimensional sphere. But the point is just, if you fold it in this way, and then this red X will just correspond to just the three components of this Berkeley ring.
Just saying, it looks like there's 180 degrees.
Huh?
It looks like it has 180 degrees.
Yeah, but the picture. Yeah, but this is some simple way to draw the picture, because the actual picture will be the right-angled regular dodecahedron. And here, each of these half of the square is just actually a pentagon, because this edge is divided to two edges. And there are 6 times 2 faces, which is 12. And actually, the actual picture is a regular dodecahedron, but I cannot draw it. And then as this folding, this red edge itself is 90 degrees as a edge of a rectangle dodecahedron. So if you just fold it, it's just 90 degrees. It corresponds to this form, index form. And the theorem just says that for any three manifold, you can say it is, you take some finite cover of this guy, and these two guys with the same thing if you forget the orbifold structure. And then you can give this guy a nice handle structure by somehow look at the picture. Here the 0 cell, and for each of the square, each of the square, it corresponds to a 1 handle, because this point will be pasted to this point. There are 6 1 handles, and then there are some complicated 12 2 handles, and I guess 7 3 handles. But it's really not easy to draw the picture. But the only thing I want to say is that this handle structure, kind of handle structure for this orbifold, is actually very closely related with the regular dodecahedron or regular icosahedron. And then for this handle structure, you just take the corresponding finite cover, and then this will lift to the handle structure of this n. And locally, it just looks like the regular dodecahedron. Okay, and then a little bit of step 2. step 2. So at first, 0 cells, maybe actually in the M0, they just correspond to just a point P in M. Actually, you can take any point you like. Any point will work. And the 1 cells in M0, they will correspond to the long geodesic axis based at P. And moreover, you need to do some just trying to mimic this picture here to just around this point P. So the long geodesic is tangent vectors is just kind of corresponding to the normal vectors of the faces of this regular dodecahedron. So the tangent vectors at P is just close to just, what is it? Maybe to just the normal of the faces of the dodecahedron. So this construction is possible. It's just kind of given by the exponential mixing, maybe not exponential, the mixing property of the frame flow. And I guess in Liu and Markovich's paper, they just mentioned some version of just you can just construct such long geodesics. So you can directly refer for their lemma instead of the original mixing statement. And then actually, you can also make sure that these long geodesic based at P are actually now homologous by still some applications of their lemma. Okay. And then what about 2 cells? And actually, this is just the point where the degree 2 comes out. Anyway. So there's some theorem in Liu and Markovich's paper. And I just kind of rephrase it to just easy for my application. So for epsilon, so we first fix M. And for any epsilon greater than 0, which is small, there exists epsilon greater than 0, which is small, and R greater than 0 is large. And for any non-homologous multi-curve, I guess L less in some Z of gamma R epsilon. So let's first just forget what is this, that this notation means. So if we have a non-homologous curve in a 3-manifold, so somehow by the boundary, it is the boundary of some surface in this manifold, whatever it is immersed or embedded. So there's some mapped in surface which has this L as its boundary. But what they showed is just a little bit more than that. Actually, much more than that. Sorry. So this gamma R epsilon is just closed geodesics in M with length minus R is smaller than epsilon, and this rotation part, absolute value is smaller than epsilon. So for any lorthodromic isometry of the 3-dimensional space, it's some translation part and it has some rotation part. And this is just saying that the translation part is very close to R, and the rotation part is very smaller than, very small, sorry. And then there exists some non-trivial invariant called sigma L, that's in Z2. And actually, which comes from, I guess, pi1 of SO3 is Z2. And actually, this is just where the degree 2 comes from, because this is somehow any element here just 2 times this guy is just 0, such that at first sigma of L1 union L2 is equal to just sigma of L1 plus sigma L2. And sigma of L is equal to 0 if and only if L bounds it bounds a certain kind of almost totally geodesic surface. And I guess in my paper I called it R epsilon almost totally geodesic surface.
Geodesic surface made out of good pants.
Yeah, exactly. But I just do not really want to define what is good pants. So this is just, if you know what is good pants, then this is just the surface is pasted by good R epsilon good pants in the, I guess, R epsilon good way.
I think the point is that every non-homologous curve bounds an essential surface. I think, but that surface may not be orientable. So I think that the surfaces you're going to use here are orientable.
Yeah, it's orientable.
But if it's trivial in integer homology, doesn't it map orientable surface?
But if it's trivial in this, I mean, if this invariant is 0, then it does bound, I think, on a orientable surface. I think that that's also.
Oh, really?
I remember well now.
Okay, it's fine. So anyway, so this is, so bound the epsilon almost totally geodesic surface, maybe oriented or orientable, whatever. And actually, you can also somehow control, maybe I call this surface S. You can control what the boundary behavior of this S along this L. So you take L as its neighborhood of L is a torus, and it just says how does S, the boundary of S, a neighborhood of the boundary of S intersect with this torus, it intersect with this solid torus. And then, I guess actually here you first construct everything for the M0. And because N is just a finite cover of M0, then you can replace everything by 0 cells and 1 cells in N. It still works. It still just take a finite cover. The image is exactly the same picture, but you just think it's just, you take a few copies of each of these parts. And then the 2 cells in the N, they correspond to the almost totally geodesic surfaces over there. Because you can control these geodesic arcs, control their lengths. And you just, a few concatenation of geodesic arcs give you a circle in the hyperbolic straight manifold, and then you pull it straight. And then you still can construct it, can control its length. And actually, you can make sure it lies in the set of closed geodesic R epsilon good curve. But at this time, maybe there are some R, some 2R, some 4R, but anyway. So they correspond to the almost totally geodesic surface. maybe these two cells is called maybe Ci, and this is called Si, with boundary of Si is just equal to the 2 copies of the corresponding straightened closed geodesic. Because here, if you just give a non-homologous curve in the gamma r epsilon, you do not know whether its invariant is 0 or 1. Some silly way you can just get rid of that is just take 2 copies. You get 0 because of property 1. And actually, in the construction, in the proof of this theorem, you can just explicitly check that there are some poor straightened closed geodesic which exactly has the invariant to be 1. So in that proof, you don't need to take this boundary of Si. It's just 2 Li. And then you just put these together. And also some pieces which just connect the concatenation of geodesics and these almost totally geodesic surfaces. Just connect something like picture look like this to a straighten. You just put something like over here. You get Z, maybe some Z prime immersed in M. And then you need to do a little bit of work to just make this SS somehow more complicated. And then you get some Z immersed in M, which is pi1 injective. And then, so since these are just more or less constructed by trying to mimic the handle structure of N over there, in step 1, you can easily construct a degree 2 map from the at least the geometric neighborhood of Z to the N2 over here. So this is more or less the idea of the proof, but not much detail. So the point here, we need to take some very kind of nice handle structure here. Is just when you arrive here, you think about what is the neighborhood of this Z in maybe some finite cover. You need to think about how does this almost totally geodesic surfaces is attached to just the union of the neighborhood of the union of these 0 cells and the 1 cells. If you take some very arbitrary handle structure, maybe the attaching curve here in the finite cover is kind of different from the attaching curve here in the N. So we need some kind of nice geometric picture to just control what the attaching curve here is exactly same with attaching curve here. Okay. So I think this is a proof, and I still have maybe 9 or 10 minutes. So let's get back to Danny's question about, for such a non-zero degree map, virtual non-zero degree map, how much volume can we kind of waste? So let me see which I can erase. Maybe I just erase this. I don't assume that the complementary region is, it has a lot of components. So actually the,
how do you define the mapping of those regions?
I guess I have erased the observation, right? Okay, so maybe let me try it here. Yes, so in the regions of M prime minus, I guess, L, so for this region, its boundary if P, maybe P is a component of maybe M prime minus L. if the boundary of P is mapped only to the boundary of P is mapped to only one boundary component of that N2, then it's just very simple, it's just pinching. So if the boundary of P is mapped to a few boundary components of this at N2, so maybe you'll first map P to just a few balls, but connected together with some maybe graph. And then you map these balls to those three handles and map these arcs to just connect them together in the three manifold N.
You take all elevations, that's too complex. 2m prime.
Yeah. Okay. Let's talk a little bit about Danny's question. So actually this so you for any maybe hyperbolic string manifold and maybe let's just restrict to hyperbolic manifold. And then we can consider all the non-zero degree maps from M prime to N. M prime is a finite cover of M. And next non-zero degree. And I guess kind of rephrase of Danny's question is consider the number which is given by the M prime simplicial volume divided by degree F divided by the simplicial volume of N. This is a set of real numbers. And that theorem over there just says that this is not an empty set. And then you can ask, what is the is inf? Right. So it is bigger. So by the, I guess by something I have already erased, this is always a number bigger or equal to 1. So its inf is at least 1. So is this inf equal to 1? OK. So there's some guess. I talked about it with some people. Personally, I think it is usually greater than 1 if M is not commensurable to N. But yeah.
So you think it's strictly bigger than
personally, I think it is strictly bigger than 1. But some people guess it's equal to 1. But anyway, but I do not have any idea about proving it is equal to 1 or not equal to 1. But there's something I can prove. So maybe one remark is, actually, this number only depends on the commensurable class of M and N, not exactly on these two manifolds. So the theorem is just, if you think about, for any closed hyperbolic manifold M, actually, you can just replace the domain to any M virtually dominates all three manifolds. You can consider about this set. There is some constant Cm. Only depend on M, nothing else. Such that for any three manifold N, not necessarily hyperbolic, and any epsilon greater than 0, the infimum of that set, I guess, simplicial volume of M prime over degree of F times the simplicial volume of N Oh, sorry. I guess here I do not really need epsilon. I need epsilon if I just state it in another way. It is smaller or equal to this C of m. So I can show that this set actually, there's a bound only depend on the source, but not depend on the target. But unfortunately, I do not have much idea about what is this number except for Gafflin's manifold. For maybe just that manifold, double of Brownian complement the Cm is smaller or equal to where is it? Okay. 24 of V8 over V3, which is more or less equal to 86.64, blah, blah, blah. So it's still very big. And if you run this theorem, actually, it will depend on the virtual domination theorem over there. So basically, that number will be, there's no bound of that number. The proof of this theorem is actually using.
So wait, once you know that there's a CM that works for one.
Yeah. Just use the virtual domination theorem, prove it works for our manifold. Yeah, exactly. That's exactly the proof. So the proof of this theorem itself is actually maybe only 4 or 5 pages.
Well, plus your.
Yeah.
Your proof that you can.
Yeah, if you assume the theorem over there, the proof of this guy is only 4 pages, I guess. It is just you just read through Gafflin's proof carefully. Actually, his proof there's some kind of bound of such number. Instead of mine, there's no such bound. Okay, I think it's exactly 5 now, so I stop here.